Okay, we're so excited to present to you the outcomes of the Ego4D, EgoExo4D challenge. This is kind of an important moment because this is actually the 5th time that we've run the Ego4D challenge. So five challenges deep now into Ego4D, and this is actually the first time we're running the Ego-Exo4D challenge. We did do a teaser challenge at CVPR 2024, but this is the first full-scale challenge. So you have the old and the new coming together here. So first, Ego4D first appeared at CVPR 2022. I think everyone's aware it's a large-scale data set of daily life activity captured in the first person. And it consists of almost 4,000 hours of video, 74 worldwide locations. And for this year, we ran the challenge against 3 of our benchmarks and 7 specific tracks. Ego-Exo4D just appeared last year at CVPR. It's hard to believe that, but it just came out last year. And this is an effort to study human skilled activities. So we capture those both in the first person and the third person in time-synchronized skills demonstrations. We have more than 5,000 skills demonstrations across the data set. And we benefit from the ARIA glasses as the egocentric capture device, which gives us like rich multimodal sensory data. And for Ego-Exo4D, we did 4 challenges and 6 tracks. We ran this from March to May on our wonderful partners at Evalii, and with generous support from FAIR at Meta, we were able to provide cash prizes to the winners of the challenge. So just a quick flow of what we're going to do. We're going to quickly synthesize the challenge, and then we're going to hear from some of the challenge winners themselves who are here with us, and then we're going to have an awards ceremony. So first with a quick synthesis. So for Ego4D, we ran the following challenges ranging from our episodic memory benchmark, social understanding and forecasting and anticipation. And for Ego-Exo4D, we covered ego body pose, relations, key steps, and proficiency estimation. I'll describe some of those shortly. So for Ego4D, we really tried to focus our benchmarks in understanding the past, the present, and the future of human daily life activity. So beginning with our efforts to study the past, we established the episodic memory benchmark, which calls upon models to isolate frames which answer natural language queries related to the videos in Ego4D. In moments queries, we try to isolate all of the instances of moments related to specific action categories that we've established. In goal step, we, along with a natural language description of our procedural steps, the task is to identify the corresponding time segment to that procedural step in an untrimmed video. Yeah. Oh no, okay. So I'm muted. Shit. Okay, okay. Okay, I see. On my own webcam? So they don't look right at me? Hello? Okay, great. Sorry for those on Zoom. Hopefully you're connected now. So, and then we have Ego Schema, which is an effort to do long-form video language understanding through a series of multiple choice questions. It's a very popular benchmark. So that takes us from the past. The present, we have a benchmark focused on understanding social interactions. So these are a series of tasks that ask models to identify when someone in a social situation is looking at the camera wearer and when they are talking to the camera wearer. So it's 2 separate tracks. Going into the future, we have our long-term activity prediction task, which given a video and a sequence of action descriptions, the model must predict the following actions that will occur after a specific timestamp. Moving on to Ego-Exo4D, we have our key steps benchmark, which In the EgoExo4D effort, we study kind of skilled activities, and so we temporally segment all of the key steps of those activities, and then we arrange them into different task graphs where we indicate whether the key step is a dependency, a mistake, or if a key step was particularly missing in a sequence of activities. So we have our fine-grained key step recognition task alongside this procedure understanding task as part of the challenge this year. Skilled human activity is like a great place to study body pose estimation. So with EgoExo4D, we have 3D key points established on the hands, 21 on the hands, 17 on the body, and our Ego Pose Challenge asks models to identify, recover the 3D poses from egocentric videos and also images. Relations, EgoExo, the first and the third person perspective, really has an extreme viewpoint difference. So in our correspondence task, we ask that models perform object-level instance matching between the ego and the exo view using the segmentation mask that we have in the data set. And finally, I think my personal favorite is the proficiency estimation benchmark, which in each of the skills demonstration, we have an annotation in which the skills demonstrator rates their abilities and their experience. And then we also have a third party evaluate their demonstration of that action and evaluates whether it's where it stands on a proficiency scale. And so in our demonstrator proficiency, we have to identify whether a demonstrator of a skill is an expert, a novice, or an intermediate. So those are all the challenges that we had this year, and we're really excited to start revealing some of the results. And first, we wanted to provide some synthesis of them. So we had 12 teams beat the baseline this year and finish the full range of what we asked people to do. They submit a task. They submit to the leaderboard, and then they submit a validation report. So we had 12 teams. They represent 20 different research institutions, and within these teams, there's 71 participants in the challenge. And I've listed some of the institutions here on the slide. We have great global representation. So when we look at the individual team members by the institutions, like the national origin of the institutions they are, we have quite a spread from Asia to North America and Europe. Interesting division between industry and academic teams. We tried to divide these between those that are 50%. Many of them are hybrid teams with industry and academic members, but we tried to cluster them. If they had more than 50%, we considered them industry team, and we had about even split between industry and academic teams. So moving on to kind of like the leaderboard submissions, we were really happy to see that not only did we have quite a lot of teams, we had a lot of submissions to the leaderboard. So these teams were also very active. And in this bar chart here, we show the number of submissions that we've received on the leaderboard. And this actually dates back to the beginning of some of the challenges. So it's not only representative of this challenge, but shows that for the Looking at Me challenge on Ego4D, since we established it in 2022, has almost got 250 submissions on the leaderboard. And EgoExo4D in body pose and correspondence are just coming online now, and we're already starting to get quite a number of submissions to the leaderboard. It's exciting to see. We also looked sort of like at the growth over time. Since it's the 5th year of the challenge, we tried to do the percent improvement over the baseline since we started. And you can see NLQ, our natural language queries test, has experienced like huge growth. Others are pushing up, like making big gains against the baseline, and still others have more room to go. We looked at this over time too, to see the growth, if there was like a year that was particularly significant, and here's the presentation of that. We did, wonder if like some of the foundational language models are really making a big impact in the natural language queries track. Okay, just a quick couple method highlights. We had some really exciting methods submitted, and we wanted to highlight some of them. The first is from our partners at the Harbin Institute of Technology. They submitted this early fusion video localization model that actually won first place on 3 separate challenges. We're going to hear from them in a spotlight talk. We also, our partners at the University of North Carolina have this wonderful approach, BIMBA, that is a spatial temporal token selector that compresses video tokens before they pass them to the large language model. And they ranked #1 on Ego Schema. And if I'm not mistaken, this is the first submission that has beaten the human baseline on Ego Schema. So not only have they beaten some of the big, GPT-4o type models, they've also now surpassed human performance, which is really exciting to see. And then we also had this wonderful submission from the University of Colorado that proposes like a flexible graph learning framework that leverages long-term dependencies in egocentric video, ranking #1 in Keystep Recognition. We're excited to have a speaker from this team today. So with that said, yeah, we'd like to turn it over to the speakers. So we were going to invite each one up to provide a short 5-minute spotlight talk on their successful submission to the challenge. And we'd like to begin with Julia Romero from the University of Colorado. Making a very dramatic entrance right now.
All right. Hi, everyone. I will be talking about our work on graph neural networks for keystep recognition. And this is for the keystep recognition task. So given a video clip, the task is to classify the action. During training, we are given the egocentric and the exocentric views, while during inference, we only have the egocentric view. Now I'll talk about the motivations for using a graph neural network. Prior methods used the keystep clips without the full video context, so they train and infer on these standalone keystep clips. With a graph-based approach, we can construct a graph to include all of the clips within the full video, such that the graph explicitly leverages the temporal relationships between the keystep clips. For example, we know that in this video, adding the cabbage has to come after getting the cabbage and cutting the cabbage. So this additional temporal contextual information helps our method perform well. Additionally, the graph is a very flexible framework, so it can leverage the paired egocentric and exocentric views during training, whereas many of the prior methods treat exocentric views as additional training samples. The graph framework is also sparse, so it is very lightweight, scalable, and it requires no pre-training on additional data sets. Here's an overview of the framework. We use the omnivore features that are provided with the data set, and we construct a graph for every video in the data set. In this graph construction phase, we create a node for each keystep segment, and we draw edges between the subsequent segments so that the nodes are ordered temporally. We average the omnivore features within each segment and use those as the node attributes. We also perform several experiments with edge connections and adding the exocentric nodes as well as multimodal nodes to the graphs. After constructing the graphs, we train a graph neural network on a node classification task. Specifically, we examine 3 graph setups. The first is the egocentric only graph, shown here. The second is the multi-view vision graph, where we add exocentric nodes for each extra exocentric view, and we draw edges from the exocentric nodes to the egocentric node within each keystep segment, and we also have temporal edges across the keystep segments. The third setup is the heterogeneous egocentric graph, where we add a new node type for multimodal data. We experimented with 3 multimodal features. The first is depth map. We also looked at object classes and narrations. We found that using the text narrations improved our performance. Specifically, this was with the video recap and Llama 3 models used together. Overall, our graph framework, which we call Clever, outperforms other methods. It performs better when it sees more nodes and more of the video. It's more efficient and lightweight than prior models. It's more effective at learning from multi-view than other approaches. And our best performance was achieved with the egocentric and text narrations setup, as shown in the bottom right. Thank you.
Awesome, thank you so much.
Thanks.
Hello, everybody. I'm Lorenzo, a PhD student from the University of Zaragoza in Spain, and I'm going to present OMAMA, the winner solution of the EgoExo4D Objects Correspondence Challenge. So the object correspondence task consists in the following. We have, for example, in the egocentric view, an object query, and our goal is to segment the same object in the target view. However, this task introduces a lot of challenges due to the drastic viewpoint transformations and domain shifts. For example, and we can see on the right figure, the exocentric view captures objects at multiple scales and covers the full environment. On the other hand, the egocentric view is very rich in hand-object interactions, but it is going to suffer motion blur and occlusions. Therefore, we require both a fine-grained segmentation and a strong cross-view semantic reasoning. Our approach is simple. Instead of attempting the complex cross-view segmentation task, we propose to reformulate the problem as an object mask matching. First, we are going to obtain a set of mask candidates in the destination view using a segment anything model. Then, through contrastive learning, our goal is going to be to select the best mask candidate that best matches the source mask. In more detail, this is our approach. We are going to take from the target image, and we are going to extract masks. Then, from each mask, we are going to obtain a local descriptor by averaging the dyno features, and also a regional descriptor by averaging the features in the bounding box, which is going to capture some regional context. Then we are going to incorporate also global information through a cross-view, cross-attention mechanisms. This mechanism, for example, is going to take the object's embeddings in the exocentric view, and it is going to apply a cross-attention mechanism with the full image features in the egocentric view. Therefore, we are injecting features from the other perspective into our object embeddings, which is going to give us more global reasoning. Then we are going to train the model via contrastive learning. By mapping the embeddings to a shared latent space, we are learning view invariant features. Moreover, during training, we are going to introduce a hard negative mining strategy. This consists in the following. Since we are in our descriptors, we are pulling the mask features, but also some features from the context. We want to encourage the model to distinguish between nearby, but also distinct objects that share this similar content. Therefore, our results are the following. OMAMA achieves the state-of-the-art in the EgoExo correspondences challenge, with very significant gains if we compare with the official baseline results. Even more, our baseline model, which doesn't have any learning parameters, it is already overpassing the baselines. Moreover, if we compare in terms of the efficiency, our results show that OMAMA is very efficient, as it is using only a 10% of the total parameters, but also just 1% of the total training parameters. So, as you can see in these qualitative results, our solution reformulates the complex cross-view segmentation task as an object mask matching across views, which simplifies the problem and achieves the state-of-the-art performance. So thank you for listening, and you can also find me tomorrow in the poster session where I will present DiffFF. And I'm in my last PhD year, so I'm happy to look for postdoc or job offers. Thank you.
And our next presentation will be from the procedure understanding task, and this will be by the team at the University of Catania, and this will be a remote presentation.
Okay, good afternoon, everyone. My name is Luigi Seminara, and today I present the Unity team solution for the Ego-Exo4D Procedure Understanding Challenge. The Ego-Exo4D Procedure Understanding Challenge involves generating graphs from procedural videos and using them at this time for reasoning. Given the history of past steps and the current key step, the goal is to infer the preconditions and the current key step, predict the next key steps, identify any missing preconditions, and determine whether the current key step is optional or represents a procedural mistake. Reconstructing graphs from videos is hard, and previous approaches are all based on heuristics. We introduce a novel framework for learning task graphs from action sequences, which relies on maximum likelihood estimation to provide a differentiable loss function. Our paper was accepted at NeurIPS 2024 as a spotlight, and it consists on given a set of sequences, we want to build a graph that is represented by an adjacency matrix. And if we could estimate the probability of the sequence given the graph in a differentiable way, we would use maximum likelihood to perform gradient descent directly on Z. So, but how we can do that? Because the sequences are not differentiable. So we can factorize the probability of the sequence as the probability of start given Z, the probability of A given start and Z, and so on. And we only need to estimate this probability, that is the probability of the current key step given the previous key steps, that we can write as the number of favorable cases over the number of possible cases. Here is an example. For instance, if we have the start has no precondition, so the probability is 1. But what's the probability of A? In this case, A is possible, but also B is possible. E is impossible, so the probability is 0.5. We can rewrite this math formula as the following, where the numerator answers the question, can I do step Ki after doing steps K with J? And the denominator answers the question, how many steps can I do besides Ki? So doing some math, we obtain a differentiable maximum likelihood loss function that can be used to learn task graphs from a dataset of sequences. Based on the proposed loss, we explore two models, the direct optimization of the decency matrix, where we initialize randomly the decency matrix, and we used our loss to learn the task graph using the training sequences, and the task graph transformer, which represents the main advantage of using our loss to learn task graph, because we can train a model that generates a task graph starting from text description of key steps or video embeddings. To tackle the downstream tasks of Ego-Exo4D, we use some rules. For action anticipation, given get a bowl and crack, for instance, we know from the graph that the next possible key steps are add water and add milk because they have all preconditions satisfied. For mistake detection, observing mix, we know that the graph that is we know from the graph that mix is a mistake because add water and add milk are missing in the past history. And for past key steps of observing mix, we know that all the previous key steps are preconditions in the graph. So given these rules and using some formulation of the math written inside the paper, we got these results on the Ego-Exo4D procedure understanding benchmark. We can see a big gains respect to the baselines, and in yellow we have the official submission that is participating to the official challenge leaderboard. Here is an example of how our method works. We start from a random graph, and then we have a refinement of the graph until we reach a graph that describes the procedure. In this case, the procedure is fix a flat tire, replace a bike tube. And here is qualitative results. So we have in orange the optional key steps. And in the right, we have a video, and inside the green oval, we have the current action that the person is performing, and then then the user will perform a wrong action. So this is wrong because all the preconditions are not satisfied for this specific action. And then we have another correct action because the preconditions are satisfied, and so on for all the other actions. So this is the qualitative results of how our method works. If you have other questions, you can reach me by mail or you can scan the core code for more details. Thank you.
So thank you so much, Luigi. And now we're going to do just 2 more spotlights. The next will be from the successful first place finish in the Ego Schema workshop and the BIMBA approach from the University of North Carolina.
Hello everyone, I'm Mohaiminul. I will present BIMBA, Selective-Scan compression for long-range video understanding, video question answering. I will talk about our method more, and I guess you already got an introduction about the problem. This is a more general video large language model, specifically focused on long-range video QA. So some of the challenges in long-range video QA is that you have to capture the fine-grained details in a very long video, and also you have to capture the high-level properties of the video. You need a long-range modeling ability for your model. However, long videos typically produces lots of spatiotemporal tokens or features, and existing method typically uses different compression strategies. To compress those tokens before passing them to the large language model. However, some of the existing compression method like pooling or convolution, they cannot capture fine-grained details. Self-attention can capture long-range dependencies, but it is very computationally costly. Therefore, in this work, we utilize Selective-Scan or BIMBA models, which is based on structured state space model. So this is defined by these 2 equations. So this is basically under the hood a recurrent model. Here X is the input, H is the hidden state, and Y is the output. So being a recurrent formulation, it has linear complexity as opposed to the quadratic complexity. Therefore, it can handle very long sequence very efficiently. And BIMBA is an improvement over the standard state space model, where parameters are made input dependent. So it has a mechanism to dynamically control your input at each timestamp. So it can selectively propagate or forget information. So in this work, we want to utilize BIMBA for long-range video modeling. Especially, we want to use BIMBA to efficiently model a long sequence of tokens, and also identify critical information or tokens from the high-dimensional video features. So this is our framework. So this is a simple framework. So first we divide videos, and we use an image encoder to extract image level features or tokens from the video frames. We concatenate all the frames and pass to the Selective-Scan token selector that I will describe next, and then we pass those compressed token into the LLM with our question to generate the answer. So here is a more detailed overview of our compressor. So given the long video, it has a long sequence of input tokens. So first we use 3D adaptive average pooling to introduce some visual queries. So here the number of visual queries are much less than your total number of spatiotemporal tokens. However, while pooling gives a good initialization for the queries, but it cannot capture fast moving events or fine grained details. Therefore, we use the Selective-Scan token selector. We concatenate the queries with the spatiotemporal tokens and pass everything together to the selector. So finally, we only extract the queries and pass those queries to the LLM along with the question to generate our answer. So and the selector has a multiple blocks, and each block contains a layer normalization, input projection, Selective-Scan, which is the BIMBA layer, and the output layer. So yeah, that's how we are doing this compression. So we also propose some video specific improvement over the standard BIMBA layers. So first is the interleaving queries. So instead of appending queries at the very end or at the very beginning, which may introduce some positional bias because the token sequence is very long for long sequence, we uniformly distribute the queries among the sequence, and this helps us to create a more balanced and uniform representation. We also utilize bidirectional scan, which is better at capturing 2D and 3D structures from the video compared to like 1D, standard 1D BIMBA for sequence modeling. So we evaluate on a wide range of video QA benchmark, starting from few seconds to few hours, and our method achieves state of the art in all of these benchmarks. And for the Ego schema challenge, we train a larger model like 70. So our 7 billion model achieves 71%, and then we trained a 72 billion model using more egocentric videos, which then we end up getting the highest performance in this challenge. So we also compare with other compression method. Specifically here we show the accuracy as a function of the number of input tokens. So we can see vanilla, which does not use any compression, or self-attention quickly goes out of memory because self-attention has quadratic complexity. Pooling and Parseval like models, they can fit in the memory. However, our model shows clear benefit, especially for longer sequence. Computation cost-wise, again, self-attention and vanilla shows exponential complexity, while our method remains low complexity with respect to the sequence length. Here are some qualitative examples. Rather than ego schema style MCQ question, it can also generate free-form answers like what are the key steps the man is performing in the cooking. So this is also accepted by the main conference and CVPR. Feel free to check out at our poster session. Thank you, everyone.
Okay, we just have one more spotlight talk, and that will be from the successful submissions to natural language queries, moments, and goal step. So this will be from a Zoom from Yisen Feng from the Harbin Institute of Technology.
My name is Yisen from Harbin Institute of Technology, Shenzhen. It's my great honor to present at this workshop today. I am going to introduce our solution OSGNet for video localization that we apply to free video localization check in the Ego4D challenge. Here's the structure of my talk. First, I will briefly introduce the definition of the free checks. Third, then I will present how we define a unified pipeline to handle all of them. Finally, I will show how we fine-tune the model for each task. Let's start with the task definitions. The main difference among the free checks lies in the form of the query. RLQ uses natural language questions, while MQ provides predefined categories named as query. GoStep focuses on style-level textual description within long videos. Despite the different query types, we unify all three as text-based video localization tasks. Our pipeline builds upon ground RLQ following a two-stage strategies. First, we pre-train the model using the NAQ pre-training strategy. Then, we fine-tune it with task-specific data. In pre-training, we adopt a simple yet effective framework, largely following the design of ground NLQ. The main improvement is replacing self-attention with members for more efficient feature interactions. The data split for all the three checks is shown following. For evaluations, we use MAP to evaluate overall localization precision across multiple IOU levels. Then we use rank at M IOU equal N to measure record at different IOU thresholds. On the MQ dataset, we started with the baseline model and it already performed very well. Our model achieved 1.79% improvement in MAP. We attribute the gain to early fusions, as our model combines visual and text inputs early on, while traditional models fuse them essentially at final classifier. For the GoStep dataset, we adopt a biasing prior strategy inspired by biasing VSLNet, which leveraged the order of stats in procedural tasks. We use the baseline architecture, but incorporate this prior and work it effectively. Our model achieved a 6.84% improvement in R@1 0.3. For NLQ tasks, we propose our OSGNet framework, which was accepted at CVPR 2025. To address the lack of fine-grained object-level information, we first introduced an in-object extraction module to capture more detailed cues from the videos. We then aggregate the extracted object features into the original OSGNet baseline, enriching the video presentations with fine-grained semantic cues. Finally, to understand the various attention dynamics, we extracted head-tuning signal from the Egocentric videos. Based on these signals, we segment the video into semantically meaningful shots and applied contrastive learning between queries and shots to improve alignment. This formed the full OSGNet framework, integrating object features and shot-level contrastive learning for robust moment localizations. More technical details can be found in our CVPR paper. On RLQ, our method achieved a 2.47% improvement in R@1 0.5. Finally, in summary, we propose a unified video localization pipeline that can calculate located moments from video for different types of queries. If you want to know more details, please refer to our code, technical reports, and our papers. Thank you.
Okay, we'd like to move on to the awards ceremony now. So we would like to just issue some certificates to those that are attending, and for those that are not, we will just announce your name and reveal your identities. So the first will be the Ego-Exo team who got second place in the correspondence challenge. Okay, not here today. Then we will move on to the first place winner, and that is the Oh Mama team first place in the correspondence challenge. Congratulations. Okay, and then our colleagues from the University of Catania winning the first place in the procedure understanding track. Okay, and then we'll move on to demonstrator proficiency. And second place, SoftBank Curiosa AI, unable to attend today, unless I'm mistaken. And the first place goes to PCI EgoExo, with all the people located here. Congratulations to you. So second place on the fine-grained EgoExo Keystep Recognition is ProVid LLM. Congratulations. Okay, and then first place is, first place is the Glover team from the University of Colorado and Intel Labs from the Great Spotlight Talk. Okay, then we'll move on to body pose. First place, PCI EgoExo, unable to attend. And third place, this is first place in the hand pose challenge, PCI EgoExo, unable to attend today. And then we'll move on to the Ego4D winners. Okay, second place in natural language queries was Gaze NLQ from the National Taiwan Normal University. Congratulations. And first place goes to HIT PCL, which was the great spotlight talk we just heard from Yisen Feng. So congratulations. This team also won the moments queries, as they noted, and the goal step queries. So congratulations on all three. They also won Ego Schema third place, And for second place, we have LPCI from Lenovo Research and a number of other institutions unable to attend. And the first place winner is BIMBA. Congratulations. Okay, the Looking at Me challenge, second place, PCI EgoExo, unable to attend. And then the first place goes to Gaze Pose Plus, unable to attend today. And then our team, our super team, HIT PCL, won the long-range, long-term action anticipation challenge. So congratulations again. And so that kind of concludes it. Those are all the winners. And we wanted to take some special thanks to Aval AI, which is a wonderful challenge hosting platform that always supports us through volunteer time. And we'd like to thank the Computer Vision Data Foundation, which hosts the Ego4D and the EgoExo4D data sets. And we'd like to also note that all leaderboards for these challenges will be reopening in the coming days, and we look forward to more submissions and more great challenges to come. So with that said, I think we'll just say thank you to all the participants, all the presenters, and all the attendees here today for your participation in the 2025 Ego4D and EgoExo4D challenge. Thank you very much.